Okay. Welcome, everyone. Thank you for joining our Delta Getting Started webinar. This is a webinar that we present every few months to help people who are just getting started on Delta or are planning to apply for time on Delta and want to know more about the Delta system and how it functions and operates and what services there are. And so today we will go through a general overview of the project, and we'll talk in particular about services and systems that are available on Delta and the programming environment and a few other aspects of the Delta project. But first, I'd like to go over some basics. Since the Access program is just kind of still getting started in the Exceed program, if we can go to the next slide, please. Sorry. We just want to go through a few items. Exceed used to have a code of conduct slide that doesn't quite exist yet for Access, but it's recommended that the code of conduct for each site be referenced to that you abide by the code of conduct that the University of Illinois at Urbana-Champaign expects for its employees and participants in programs as part of the Illinois system. And I've also included a paragraph here, which is a bit small text, but this is the draft code of conduct from the Access program. And so if you find that there are people that are not abiding by the terms of the code of conduct, please let us know. At some point, Access will have a list of ombudsmen and people who are responsible for following up on code of conduct violations. And so please contact us if you find that any of the participants, either the presenters or attendees, are not abiding by the code of conduct that we have here. All right, next slide. Right, so we have here what I just introduced already, which is the quick training outline. So we've broken this down basically into 4 different sections. Brett Bode, who's the Delta Executive Director, will go over the introduction of Delta, the Delta system, and then he'll go through some of the details about the node architecture and the interconnect things that you might want to know about the various options for different GPUs that we have and what you can expect for performance. And then I will go through and talk about system services and features. And then finally, Galen Arnold will wrap things up by discussing the popular topic of the Delta programming environment. All right, so just as a reminder, if you have questions, options are to post them in the chat, and Delta staff will try to address those in real time. And at the end of each section, we will also give some time for people to raise their hand and ask some questions as well. All right, thank you very much. So Brett, why don't you go ahead and get started?
All right, well, welcome everyone. I'm hoping you're already on Delta or maybe considering preparing a proposal for Delta. We are certainly happy to be NSF's newest production resource. We went into production just over a month ago, so we're very recently in production. We have quite a few projects that have already ramped up production and are burning through their time quite quickly. So we encourage that, and of course really look forward to seeing many of you and new projects in the system as that happens going forward. So I'm going to give kind of a brief little introduction to Delta first. So from the time of the proposal, we had 3 main thrusts with the project as a whole. Of course, we're providing a compute and data resource, but we wanted to orient that compute resource towards being a GPU-oriented system, so and furthering adoption of GPUs with the Delta resource. We noted that many of the existing, well, pretty much all of the existing resources at the time within the NSF portfolio had the model of having a few GPUs on a largely CPU-based system. So with Delta, we've tried to turn that on its head and provide a very GPU-oriented resource with some additional CPU resources that can fill in the gaps where you have codes that don't have GPU alternatives. On the data front, we're certainly providing large and fast data, but we're trying to also provide interfaces that move beyond POSIX, and I'll talk a bit more about that in a bit. And finally, we're also looking to improve interfaces. So certainly we have the traditional SSH command line there, but we're looking to broaden that into other ways to allow people who aren't familiar with command line interfaces to make productive use of the system as first-class citizens within the user community. So how do we provide those interfaces and what should they look like? Those are all important parts of the project. So on the compute side, I already mentioned, really we're focused on GPUs. So we have enough CPU resources to meet additional needs, but our focus is on getting work ported to the GPUs so you can get the most bang for your buck. And certainly we will also want to take existing codes that are already on GPUs and improve them if that's possible. We certainly recognize that porting an application to a GPU is not the same as porting an application between CPUs. The GPU architecture is quite different, and there are many challenges to achieving a reasonable, a decent level of performance on the GPUs. So certainly that's something that we want to help. If your team is interested in looking into that, certainly let us know. On the data side, as I said, we're providing large and fast file systems, but we want to move to a relaxed POSIX environment. And what we mean by that is that your codes may not have to change. They may be able to use the traditional POSIX APIs that you already are familiar with, but behind those APIs, we may not be providing the normal guarantees of POSIX, and that has to do mostly with locking. So if you're opening the same file for writing by multiple processes on multiple nodes, that requires a lot of locking to synchronize the defined order of when writes get written to the disk, and that slows things down. And we believe that most, if not all, codes can operate without those guarantees and improve performance quite a lot. So talk a little bit more about what we're doing in a little while on the hardware description. On the interface side, we're partnering with the Science Gateways Community Institute to develop different interfaces. So certainly that would imply, and certainly correctly imply, that we're deploying science gateways, and we are nearly ready to make our first main science gateway move into production, but we also want to support other existing community gateways. So if you have one of those or interested in seeing a gateway that you know of be enabled on Delta, also let us know. We are interested in helping you make your gateway work there. We are still learning how to make that all happen, but we are doing our best to provide both the access and the job turnaround and other things that gateways need to be productive and have happy users of the gateway community there. So the other part of this is that we also want to improve accessibility, and that's more for people with disabilities that may need to use special tools to utilize systems, and we want to make sure our interfaces are as accessible as possible. That's certainly not been a strong component of past projects in computing for HPC, but we think it's something that's very important to enable a broader community of users to make use of the system. And our vision for our science gateways is that we provide our own, but we also want to enable as many community focused systems as gateways as possible. Mostly, of course, that's because we want to leverage work done by others, and we definitely want to encourage the use of gateways wherever they make sense. We're considering a variety of new gateways. We've had suggestions of an AI-oriented gateway, and so if you're interested in that, let us know. There's been suggestions that we should be hosting some standardized data sets. We would like to hear from you if that's what you would like to see. How would that work for you? We're very interested in understanding your workflows and how that might be met by a standardized gateway interface, either for regular research computing or even classroom sorts of computing work could be enhanced by the use of gateways or that sort of thing. All right, with that, I'll change gears a little bit and talk about the node architecture and interconnect. So these are basically the hardware components of the system. So the high-level overview of the system looks a bit like this. So we have several different node types within Delta, and those have different partitions when you're submitting jobs. On the GPU side, we have 100 quad 64-bit GPU nodes. Those are A100 nodes. We also have 100 quad A40 nodes, which are a 32-bit variant of the Ampere silicon from NVIDIA. And then we have a handful of dense GPU nodes that have eight A100s in them, but they also have large memory. We haven't explicitly called them our large memory nodes per se, but they more or less meet the qualifications that most other sites use for that sort of thing. We also have, as I mentioned, a number of CPU nodes. So we have 124 dual socket CPU nodes. All the CPUs within both the GPU and the CPU nodes are the same model and of the AMD Milan processor. All are 64-core AMD Milan processors running at their highest clock rate for that part, which is using the 7763 part number. So they give quite good performance with a large core count, a large number of threads. Overall, the combination of these systems gives us just about 10 petaflops of double precision performance, 100 petaflops single precision, and 200 petaflops potentially on tensor ops. We're augmenting that or supporting that with 7 petabytes total spinning disk storage made up in 3 luster file systems, and a 3 petabyte flash storage system that's currently operating as a relaxed POSIX cache for our scratch file system. I'll talk a bit more about that in a minute. So I already mentioned the workhorse of the system. The main highest performance and largest number of nodes are the quad A100 nodes. There's 100 of these. The GPUs are NVLink connected and are water cooled, providing a very solid performance regardless of the workload on the system. Each of these nodes has 256 gigs of RAM and 1.6 terabytes of solid state or NVMe storage. So these are probably your main workhorse, particularly if you have double precision GPU sorts of codes. On the same basic node architecture, we have a quad A40 node. So we have 100 of these as well. So these use the same Ampere silicon, but they've removed most of the double precision capability on these nodes. So you really don't want to use these for any sort of double precision work, but they have pretty good single precision performance. In fact, certain non-tensor op based single precision performance is actually better than the A100. So if you happen to be in that particular narrow scope of GPU codes, that might be a very good match. These also have unique ray tracing capabilities that the A100s do not have. So they provide good performance on 32-bit and AI sorts of workloads, and some unique capabilities as well. So we do encourage people to check these out. They are part of the reason that we included these is they have a lower cost than the A100 nodes, and that allowed us to put more total hardware on the floor. Because they're lower cost, we also charge less for these nodes. So even though they're slower, you may find them to provide, hopefully, similar performance for your allocation SU, so to speak. So if you want to compare the performance directly, you find that typically the A40s are similar to a V100 if you have any experience with those. But they aren't, because they're not NVLink connected, their scalability is somewhat limited. So it's going to depend on what types of code you might want to use for these sorts of things. We also, as I mentioned, have the GPU dense nodes. These are 8-way A100 nodes, fully NVLink connected. They have 2 terabytes of memory, so they are by far our largest memory nodes as well, and certainly qualify as large memory in comparison to most other NSF resources as well. So these can be used for either GPU or larger memory work, depending on what you're doing. But one of the things I should have mentioned and will be mentioned later is, of course, there are 2 types of allocations on Delta. One is CPU, and that's applied only to the CPU nodes. and the other is GPU, based on GPU hours, and those apply to any of the GPU resources. So even if you were only using CPUs to get access to the large memory nodes, you still are using GPU allocations to access these. So these are very high performance, high capability nodes. So we have a small number of them. There is a premium charge for these nodes, modest premium charge for these nodes, but they still might meet your needs if you have a workload that doesn't scale between multiple nodes beyond on the quad nodes that we would expect to have the larger resources in use. We also have a single AMD MI100 node. This is very similar to the quad A40 nodes in architecture. These are 8 MI100s, PCI cards, though they are stacked in 2 sets of 4 connected with AMD's Infinity Fabric. This is a large memory node, however, so if you were interested in getting access to large memory, but not paying the full cost of the dense GPU nodes, this would be a good option for you because the charge rate for this node is a bit lower than the dense nodes. But this is also a good place for you to, if you want to try out ROCm and the AMD ecosystem and porting to the AMD software stack. This is a good place to try it out. The MI100 is, of course, not the high-end card that is now the MI200 or MI200 series that you'll find in big systems like Frontier at the Oak Ridge Leadership Computing Facility. But it is same basic architecture and the same software stack. So if you want to try porting over, try running on these sort of things, this is a good place to try. The performance of it is, it's okay. It's probably closer to an A40 than it is to a A100 in most specs, except that it is double precision capable. So you can run double precision codes on it in addition to single precision or tensor sort of ops sort of based codes. But it's not as performant as an A100. Of course, it's also less expensive, so it's there's some benefits there as well. So the CPU-based nodes, as I mentioned, are very similar. The only real difference is they have two sockets, 2 AMD 64-core processors, 256 gigs of memory, and a slightly smaller NVMe drive in each node. But we do have good scalability with these. So if you have CPU-only workloads, these are very capable nodes. And at the moment, probably among the most capable nodes within the NSF portfolio, even on the CPU side. Our utility nodes look very similar. Actually, the only real difference from a architecture point of view is that these are much less dense. The CPU nodes have four 2-socket servers in a 2U enclosure and are water cooled, whereas the utility nodes have a single 2-socket server in a 2U enclosure that's air cooled to allow us to have more space for cards and things like that. So we can put extra NICs in these to provide more throughput for network traffic and things like that. So these are where your logins are, where your Globus data transfer nodes are, and eventually we'll also offer capabilities for you to run persistent or at least long-running tasks that are not necessarily tied to a specific job. So we're still working on architecting that solution. So it's not quite ready yet, but that is our intention, is to provide some capability for workflow engines or other sorts of things on those sort of systems. At the moment, though, if you're running on a login node, it has all the usual limitations. While it's a capable node, anything that's long running or using lots and lots of memory should be run on a compute node instead. So, and if you use something too significant on there, it'll probably be killed, and you'll be told to move it to a compute node. Our storage environment starts with our spinning disk system. So we have 7 petabytes of total spinning disk. 6 petabytes is available in locally attached DDN storage appliances that split between 2 petabytes for home and 4 petabytes for Scratch. The Scratch file system is also twice as fast as the home file system. the remaining petabyte is remote mounted on our center-wide file system. That is where our projects file system is located. So that has some space for every project, but we do currently encourage all large and active data sets to try to be pushed onto the Scratch file system. Eventually we may enable purge on Scratch, but today we are not. So we don't have any need to do purges. So we're encouraging active use of the Scratch file system in preference to pushing stuff onto projects, which is a more space limited area. The other reason for pushing stuff onto Scratch is you can potentially use our flash storage environment's disk cache. So right now, the way we have this 3 petabytes of flash configured is as a cache for the Scratch file system. It has its own mount point, which is /IME. But if you look in /IME, you'll see the same namespace as you see under /Scratch. And if you write data into IME, it will eventually get written actually out to Scratch, though that doesn't happen it doesn't happen quickly. So and if you read data through IME, it will load it into the cache from Scratch and then make it available. Eventually we're going to be deploying a new file system from DDN called Red, which has even more characteristics that we'd like to expose to users, including a more object store like interface and a more performant flash file system that will be standalone rather than acting as a cache. But for now, IME is what we're using for this. And if you have workloads that have a lot of rereads, this would be something that we would be interested in you trying out. And you might drop us a note letting us know of your interest, and we can provide more information on how to make good use of it. The network interconnect is provided by a HPE Cray Slingshot arrangement. I think we are currently the only Slingshot network, I think, in the NSF portfolio. The larger systems at the Department of Energy laboratories are pretty much all Slingshot, or soon will be anyway, as systems get deployed. But we're one of the few small scale systems even from HPE that has chosen to go Slingshot instead of InfiniBand, and part of that was to see how it performed. In principle, we got a good deal on Slingshot. It provided twice the performance of the InfiniBand network we would have gotten, and it has some interesting characteristics which we are still exploring. The current setup is all the nodes are connected with a temporary 100 gig NIC to the Slingshot switches. We have hardware and now are just getting the software we need to upgrade those to 200 gigabits per NIC. That will require a hardware and software update. That probably will happen in the December timeframe, and we will have more information out to users as that happens. It's not something users will have to be aware of when it's done. It'll just we will have to rebuild software stacks and let people know that they'll have to relink their codes when that change is made. But other than that, you don't have to be aware that that the hardware is changing underneath of it to provide more performance. Beyond that, we should note that our compute nodes do connect directly to the through the bridge switch to an external network. Our compute nodes do have external IPs and can talk to the outside. They do have firewalls preventing externally initiated connections, of course, as you might expect. But within batch jobs, you are able to connect directly to outside services without any particular issue. We have a total of 200 gigabits of connectivity between the compute nodes and our utility nodes and the outside network. So we believe we have adequate network bandwidth to meet pretty much any network need from either utility nodes or the compute nodes themselves. So if you find a problem, let us know, but we think we've got it pretty well architected to support the external network needs. with that, I will turn things over to Greg, though we're going to switch presenters. As soon as I find it.
Stop sharing button. That's right.
Yeah, well, my mouse keeps disappearing right as I get to the place it should be. So why is it?
Okay.
Sorry about that.
All right. So there were a few questions that came in, and I think we addressed them. But before we transition, while we transition to the next set of slides, are there any questions for Brett? And if you have them, feel free to raise your hand and unmute yourself and ask the question or post it in the chat. All right, it doesn't look like there are any additional questions. I think we've clarified most of the questions in the chat, but I think what we might add to our content is a little better description about how Delta itself is allocated and the various opportunities for allocations and for things. And there were questions about fee-based access to Delta, et cetera. All right, so thank you, Brett, and I will continue on. So my name is Greg Bauer, and I am a co-PI on the Delta project, and I am responsible for making sure that Delta provides the right services and has the right kind of programming environment for you all to use. And I also help orchestrate or organize the user support aspect of Delta as well. All right. So how do you get onto Delta? So this, it's a little confusing because access has now become an overloaded word. With the new access program, it used to be resources used to be allocated through what's called the Exceed program that NSF funded, and that was reconfigured and recompeted and is now part of what's called the access program. And sometimes it gets a little confusing talking about access to a system from access. So the most common interface, as Brett mentioned, to get onto Delta is through directly logging in through Secure Shell SSH, which we highlight here. There was some confusion for a while we were transitioning off of Exceed into the access program, where there was an ability to log in through what was called a single sign-on mechanism that Exceed supported. That is no longer available. However, the access program is planning to provide a similar service as well at some point. At the moment, that is not available, but this is the most standard way to access. If you're comfortable using or prefer to use a web-based interface, we do support Open on Demand, which I'll mention later in the slide deck. And it also offers a terminal or command line interface to Delta as well. So there are at least two different mechanisms for logging in and interacting with Delta. And then also the Science Gateway, which isn't in production yet, but that's something that we are working on, and it will also allow some access, but maybe a little bit more limited. All right, so Brett mentioned the key file systems. We do have three primary file systems that are provisioned through Lustre. There's the home file system, the projects file system, and the Scratch file system, which we talked about. And it was noted in the chat that we have not yet enabled purging, but the Scratch file system, once it reaches a certain threshold, will have purging enabled, and we will make sure to communicate in advance when that happens to make sure that people are not caught off guard. Delta itself does not provide an NCSA, doesn't provide a readily available long-term archiving solution for all users of Delta. NCSA does have some other storage options called Granite and Taiga. One of them is a spinning disk system and the other one is a tape archive system, but those are based on a cost use method. So you have to provide some funds to get storage space on those systems. As Brett noted, each compute node has a locally attached drive, NVMe drive. It's called /temp, and I think he mentioned that through changes in the namespace, you don't see a general /temp like you used to see in the olden days. You just see your own /temp. It is a shared resource. So depending on how the node is shared amongst other jobs, you may be competing for use of the /temp system, but it is good for very quick access times for many small files, for example. The one thing is if your job ends, you will no longer have access to that space and it gets removed from the NVMe, locally attached NVMe drive. And Brett did mention for the time being, we do have this IME drive file system, which is based on Flash, as it functions more as a cache, and we'll talk a little bit more about that in a minute. Sorry about that. So how do you know how much space you have on the file system? So we do support a general quota command, and it talks to Lustre and aggregates your totals or summarizes your totals based on every project that you are a member of. The user or home directory is not based on a project quota, it's your old individual quota. And so it'll just be listed there by itself. And then for each project that you're in, you'll see a listing for the space on the projects file system and space on the Scratch file system for totals. And if you're a PI and you want to know more information about how your team members are using the different spaces and projects in Scratch, we don't have a simple tool yet to enable that, but we can show you some methods for finding who's using most of your space on your for your different quotas for different projects. And if you do have storage constraints that you believe, so if when you write a proposal, you're supposed to specify how much Scratch space you'll require. And if you find yourself coming up against those quotas, we do entertain short-term increases in the quotas. If you send us an email, we'll let you know what to do to make that request. A few specifics about our Lustre file system on Delta, or the Lustre file systems on Delta. Probably the key one that used to be a problem for early users of Lustre, which is a large parallel file system, is what's called striping. So in the past, when you created a file on Lustre, it would put it across what's called an object storage target, and which is effectively like a disk drive. And depending on how big a file you had, you may need it was desirable to spread them across multiple drives. This is now handled automatically. You no longer have to deal with that. It's very helpful for you to get good performance. It means that the drives are filled up more uniformly, and in the end also can result in better performance. And since it is Lustre, there are a large number of best practices or recommendations when you're using Lustre. A couple of them that we highlight here. One is to avoid putting links between the different file systems. So in the past, we would put symbolic links between projects and Scratch from your home directory. We now prefer to not do that, just in case if one of the file systems has a hiccup, that you don't end up doing things like listing a directory that has a link, and then that link will that listing will hang. We also recommend not creating too many files in any single directory. Lustre has some limits on how responsive it is with what's called metadata for listing all the contents of a single directory. So try to limit the number of files in one directory to a few thousand, and then make a hierarchy of directories. And if you have tens and hundreds of thousands of small files, we recommend you use technologies or solutions that can aggregate those into a single file, something like the hierarchical data format of HDF5, or using containers, for example. If you can put all your data into a container, you can mount that container and access the files that way. That really alleviates the amount of load on our parallel file systems. And we're happy to work with you on implementing those methods. So for the time being, while we are working with DDN on our future RED project, which will allow for the object store approach to data storage, we have this IME Cache system for Scratch, which Brett highlighted. We have some documentation on our NCSA wiki, which we linked to from our user guide. And in principle, you have the ability to write files to the cache. And if you do things in such a way that you can avoid flushing the contents of the cache to the backend file system, which in this case is Scratch, you can actually get quite good performance and lower the load on the backend file system, which is the goal and design of this. So if you're interested in this and have questions, go ahead and check the user documentation that we have for this, and then let us know if you have specific use case questions. You can always send us an email at help@ncsa, and we will be happy to help you. One thing that might be a little bit unique about our file systems directory setup at NCSA is we have a bit more aggressive access control policy for your home directories and your shared project spaces. In the past, you will be able to open up your home directory and share it with whoever you'd like. We have found that there's been many times unintentional sharing of data that people probably don't intend. And so we now control at the root level of the directory structure that disable your ability for sharing your home directory, period. We encourage people to share the contents of data and files within members of their own project through the project space or the Scratch file system, the project file system or the Scratch file system. If you need to share data between different projects on Delta, please let us know, send us an email, and we can help you enable, we can enable methods that will allow you to use some extended attributes to share between groups. If you need to share externally with someone outside of Delta, who's not on the system, you can use Globus Online, which we don't document here, but we do, hopefully we'll be able to set up Globus Online sharing for contents hosted on Delta itself. One thing to note is you are not able to share through /temp anymore because of the namespace approach. So that is one of the challenges, but it also makes the system a bit more secure and an unintentional data sharing. This is the next topic here is the common user environment. This is something that was developed during Exceed that we also carried over into Access. It's a set of environment variables that make it easier to set up job scripts, for example, or workflows to use commonly named environment variables that allow you to transition between different resources like Expanse or Anvil or Delta with minimal changes to your scripts and code. So, for example, some of those are only accessible when you're running a job, for example, because they depend on which project you are currently running on, because you might be a member of more than one project. And so we just show here and highlight some of the environment variables that are available through the common user environment. This is documented on our user guide, and also there's good documentation for the definitions of these variables for things like node scratch, parallel scratch, your home file system, etc. So running jobs, we've already had a few questions about how you get charged for jobs and if there are different project charges or partition charges. So I don't really go through them here because we hope that you'll go and refer to the online user guide for the differences in all the partitions. But the couple of things that we want to note is that the charging, as Brett mentioned, is somewhat based on relative performance to our within a given type of system, like GPUs, for example. So all the GPU partitions that have a different charge factor in front of them, that's based on a roughly relative performance to the GPU A100 node. For example, the MI100 node has got a different charging compared to the GPU A40 node. There's also a difference in charging if you need interactive or short, quick access versus running in the standard partition. You pay a little bit extra to have the immediacy of this interactive capability. One thing we note is that the default for node use is shared. So if you need to use one GPU with a few cores, maybe 3 or 4 cores to drive that GPU, you'll be sharing the resource with other jobs that might be doing similar levels of use of a node. So you may not need a whole GPU. And so Slurm does its best to try to allocate cores and GPUs that are close to each other to avoid contention for shared resources, such as access to the DRAM for the CPU or the bus to the GPU. But it's not perfect, and there'll be situations where you might see some run-to-run variation. If you submit the same job over and over again, you might see a variation in runtime because of who else is running on the compute node. One thing to note is we don't have a default account set up for your project, so you will need to specify an account to Slurm for charging, and that charging will be on which projects you are in, and you can use the accounts command to list all the different CPU and GPU projects that you have time on. and that you can charge against. And those are going to be used when you set up your job scripts, either through regular batch processing or through open on demand. And you have to know what projects you're part of, and make sure that if you're going to submit a GPU job, that you use the corresponding GPU project as indicated in this example here, with bbkw-delta-GPU would be used for GPU jobs. And if you had a CPU only job, you would use bbkw-delta-CPU, for example. And we do support interactive access. I don't have the full discussion here, but we have some sample shell scripts that let you look at how to quickly set up an strictly interactive job by putting a bash shell on a compute node. And also for convenience, if you have a job running on a compute node, you can also SSH directly to that compute node and take a look and see how your job is running, see how much memory it's using, etc. Now, this is a new topic that we didn't include in our previous getting started presentation. This is the billing and charging. So when there's a charge factor for what partition you're going to use. There's also the computation of what you get billed for. So when you ask for a certain number of cores and a certain number of GPUs and a certain amount of memory, there's a fairly straightforward algorithm that decides what you should be billed for. And the billing is going to be based on the maximum of any given resource unit, which we're going to call an RU to help distinguish it from access, or it exceeds use of what was called the service unit, SU. So I have two examples here to help you understand how Slurm is deciding what the billing should be. And it's based on what's available on a given node. So I'm not going to go into a lot of details here, but there's some simple math. And basically, it comes down to computing the maximum resource unit that would be responsible for providing the resource that you need. So for example, if you're going to request 2 CPUs or 2 cores and 50 gigabytes of memory on a CPU-only node, we'll note that 1 CPU is equal to, or 1 core is equal to 1 resource unit. But with 128 cores or 128 CPUs and 250 gigabytes, there's roughly 0.512 resource units per gigabyte. So if you were to use and ask for the whole node, you would be given all the memory. But if you're going to use a fraction of the memory, you're going to be billed the proportional fraction of the cores that would be associated with that much memory. It's a little confusing, but that's the basic idea. So you get billed for what you ask for based on the resource unit of that type of node. So for the CPU, it's C cores, and if it's a GPU node, it's the GPU. And we have another example over here on the right-hand side where you ask for 1 GPU, but you ask for 32 cores. Let's say you have a problem where you also have a lot of threads that do a lot of computing to keep the GPU busy, but you only need 10 gigabytes of memory. So here, 1 GPU would be charged for 1 resource unit, but the 32 CPU cores on that GPU node would actually be responsible for 2 GPUs or 2 resource units. And the memory turns out to be a small amount and only contributes 0.16 resource units. So in the end, your Slurm billing would be based on the 2 GPUs or the 2 RUs for that job. And then you would have to factor in the partition charge, which we talked about a little bit earlier, and the amount of wall clock time. So that's a lot of information. The math isn't too complicated, but it kind of gets a little confusing at times. And so I also include 2 examples here, how you can use Slurm to print out what it computed for your billing factor, and how you can then translate that into an actual job charge. We're going to provide some scripts later on that we haven't put them out yet that will do this for you. And there'll be some equivalent ones that the Access program will want to have enabled as well, called Access Usage, which will help you understand that information as well. But so I won't go into detail here because it's going to take too much time. But for reference, I recommend that you go look at these and try to follow along. And if you have questions, please let us know and submit some tickets to us. And we'll put this information on the user guide. It's not yet on the user guide. We just kind of created this recently. All right, we talked about running jobs already a bit. We talked about support that the system is default for shared node. If you know you need to use all the resources, but you don't want to specify all the resources, you can use the -- exclusive option to Slurm, which is very helpful if you know you're going to use all the memory, for example. We also support X application support from compute nodes. So you can do X11 forwarding from a Slurm job running an X-based application from the compute node. Not really recommended for people who are thousands of miles away and trying to do X applications without using a VNC type approach, but we support that in principle. And as I mentioned earlier, you can SSH to a compute node in your job, and we kind of highlight here how you can simply print out from Slurm to figure out what nodes are allocated for your job, and then you can SSH to that job. If you only have one job on that node, you are put into the same runtime environment, basically, of what processors and memory limits that you have, so that you can look at your GPU usage and your memory usage. For those of you that do a lot of Python development, which is probably most of you, we support Jupyter, and we have two different ways of providing Jupyter. One's through the classic approach through the command line interface, setting up the Jupyter server, and then attaching a browser to it externally, or the simpler way is through Open on Demand, which a lot of people are starting to adopt and use. We also support containers. Galen's going to highlight that in a bit. The key here is that we provision a lot of these containers for you already on our file system, so that you don't have to have multiple downloads of very large containers in your home directory or your projects or Scratch directory. We try to keep up to date and provide the latest versions from NVIDIA and AMD. This also allows you or us to also give you access to older versions, or if you want to pull them down yourself from the container repositories. Let's say you need an old version of TensorFlow from 2018. We're probably not going to install that for you, but through containers, you can go ahead and pull down that version yourself. And here's an example. We do allow running containers from the login nodes. If you need to do some testing and development, you don't have to run them from a container, from a compute node, except that we don't have GPUs on login nodes. So if you need to test a GPU-enabled container, you'll have to do that from a batch job, which is quite simple to do with our interactive use of our compute nodes. And then finally, how do you get your data onto Delta? We support Globus online data transfers, as well as the standard use of SCP, FTP, GET, curl, and wget, etc. Our recommendation, though, is if you're moving large amounts of data, that you use Globus. It's by far the best solution for unattended data transfer. Globus makes sure that you get your data transferred. And as long as you have the disk-based quota available, it'll keep moving your data over. The one thing I would note is that people who there's two authentication methods. If you want to use your NCSA identity, you can use the NCSA Delta endpoint. And if you want to use your access identity, for example, to authenticate to the endpoint, then you have to use the access Delta endpoint. If you're going to use the command line methods like SCP, GET, curl, etc., and rsync, if they are long-running transfers, we recommend you put those in a compute job so that you don't degrade the performance of a login node for everyone else. All right, so I rambled on through a lot of details of the system services and functionality for Delta. And if there are any questions, we should take a quick break. And then Galen will take over. Are there any questions that we can address here that didn't get addressed in the chat? All right. Looks like Abdul has a question. We can see if we can address that real quickly. Is there a way to find out resource use of each user in a project? Let's see. You can do some analysis of usage from Slurm jobs. Yes. So you can do that. You can look at job history for a project. You can do that. Let's see, Anna's asking more about the Globus endpoints. I guess Anna, I would say that we provide the Globus endpoint. You would need to refer to the Globus documentation if you have specifics about how Globus works. We're happy to help you use Globus. We're not necessarily Globus experts, but the basic functionality for basic file transfers, setting up collections and stuff like that, we can assist you with. But if there's some additional details about how Globus works, we would, you could ask us, and if we're unable to ask you, we would probably defer to you sending a question to the folks at the Globus, like globus.org. I hope that answers your question. All right. And then Globus also does more than file transfers. It's expanded into many other areas for coordinating workloads and workflows, and it's used now for providing other aspects of even gateway functionality. So it does a lot of things. So, let's see. Maybe this one about talking with Radiant. Yeah, okay, that's an NCSA resource. So maybe we can take that one offline and see. Is there any? Oh, they're coming in fast. Galen got that one. All right. What's the ease of installing a new program? Do we go through? Oh, okay. Well, that's a good transition. John Paul, thank you for.
I'll take that. I'll take ease of.
Yep. So I'll silence myself and we'll transition to Galen Arnold. Thank you, Galen.
Greg's got the slides still, so you'll hear me say next. And in trade for Greg doing the slides, I'll keep an eye on the questions as well, but others can chime in with typed answers. So, programming environment. We're using SPAC to set up the programming and compilers under two trees for you. So there's two trees that look similar, but they're not mirror images of each other. But we try to replicate things that make sense. So things like compilers, if it makes sense for a compiler to live in both CPU and GPU side, and math libraries, HDF, stuff like that. So for example, the GPU side has NVIDIA compilers where the CPU side does not, because we look at the NVIDIA compilers as more targeted towards supporting the GPUs. And we'll talk about both compiled languages and Python. I'll endeavor to stay within the exceed access code of conduct while I talk about Python. That'll be my mission for this talk. And then containers, we'll say a little bit about that as well. So I think I got everything on that slide. Oh, we do like containers for Python. Yeah, next. So about Python, we have for supporting Python environments and installing things yourself, we have got you started here with three flavors of Anaconda. And what we did early in the system is we just pulled the latest Anaconda from the Anaconda site. So this is the same Anaconda you would get if you installed it yourself on your desktop. It's Anaconda 3, and we did recent updates to it as well. So it's actually pretty fresh as of going into full production. We had a JIRA issue where someone asked us to update parts of Anaconda, and we ended up updating most of it. So there's a flavor for CPU and GPU. These all include Jupyter within them. So that would support setting up your own SSH tunnels. And it's also the Jupyter that's on the back end of Open On Demand. And then recently we also added a Anaconda 3 for the MI100 AMD GPU node. How these differ is when there are options for installing a Python package with GPU support. And when we say GPU, I'm talking about NVIDIA, or MI100, which would be ROCm, then we specify those install flags for that Python package and stick it in that Anaconda. So otherwise, they would have the same versions of something like Matplotlib or other common things. But there might be differences where the GPU one has, let's say, GPU flags were set for the PyTorch install, or maybe the Numba. And then we also have containers. The various containers from NVIDIA and AMD's Infinity Hub have Jupyter in them, PyTorch, TensorFlow. So there are containers with those names in the container that you'll see under our software external NGC directory and software external MI100 directory. And look there for containers before you go to download one yourself. we probably have the current versions of a container going back over the last couple months. So there's no need for you to store that in your home directory. We've already pulled it for you, and you can go explore it from the login node by just starting it with apptainer and looking to see what's in it, see if it has all the pieces that you want. Real popular thing to do with Python that I've done in answering JIRA issues is I'll go look in a container, apptainer, run container name, and then just do a pip list. Once I've got that container's Python loaded in my prompt, a pip list or a conda list will show me what Python pieces are in that container's version of Python. And then lastly, we have a Python that's just on the system that's not in Anaconda. It's not in a container. It's just the newest Python. If you want to start from sort of a clean sheet Python, then just module load Python and you'll have 3.10.4 and you can do your own virtual environment from there. There's no one right way to do Python. And we're not trying to say, do it this way or that way. We're here to help you. And so back to the question of installing software. So we would prefer that you try to install software yourself and then contact us as you run into problems. We're not crazy about the type of inquiry that says, please install all my software for me. We want to see you try. It may be that if the question comes to us or the demand, please install all of my software for me, we might reply to you, here are the links to how to install your software. Please try these commands first. We kind of try to follow the approach of teaching a person to fish here. We think it's good that you know how to maintain your own software stack to the extent possible. But if you run into any kind of issues, don't pound your head on the wall for a day, getting frustrated. If it's taken you more than half an hour to get something working and you just keep getting errors, that's time to reach out to us because we may be able to get you over that hurdle quickly. So please reach out. Next. Customizing Python. Again, we're not telling you one way to do it because Python has multiple ways to do it. I use all three of these, and I'll give you a little bit of my thoughts about it. Also, the link at the bottom of this page, the comparison shows some good insights into strengths and weaknesses of different approaches. So pip install is the recommended Python installer from the Python folks that develop and support Python. We use that with the Python module, and we tend to use that against containers with -- user. It'll install it in a subdirectory of your home directory. Advantages of pip is it's fast, and it usually works the way it says it works. Disadvantages of pip are that if you're using pip and intermixing it with conda, conda won't necessarily keep track of things that pip did, and you can end up with a conda environment that's not easily solvable down the road. It can make conda issues pop up later. VENV is the Python way of making a new virtual environment, and that's a good way to go. And then conda environments, creating your environment with the conda commands is also a good way to go. We conda install things when the recommended way of installing that Python module is via conda. And some things like to install via conda. Other things recommend installing via pip. So I tend to follow the documentation of PyTorch or TensorFlow and do what their documentation suggests. Conda environments tend to maintain a better state, I'll say. Conda strives to make sure that everything's consistent within your environment, and that's what it's doing when it goes into that little spinning wheel of solving environment. Now, the downside is it's sometimes the case that you'll try to install something big with conda, and it may not finish in hours. And it could be that the same thing would install via pip in 5 minutes. So you kind of have to weigh those against each other. I'm still figuring it out. Next. Profiling tools. So for the NVIDIA GPUs, we have NVIDIA Insight systems, and it is up and installed when you have CUDA loaded. This is working at the moment by doing a sampling of your CUDA library calls. We don't have hardware counter support at the moment. That's an issue we're internally discussing. It has security implications, and that's just not there yet. You have to remember that this is a shared resource, and other jobs could be running on the same node as yours. So there's other concerns there that we have to look at on the back end. But the sampling of the library calls turns out to be fairly useful and effective. So if you want to use Insight and are happy to look at, percent time spent by things like memcopy from host to device and device to host, and how much time was spent in kernels, it'll definitely show you all those things without needing the hardware counter access. So that's there and ready for you to use. And you can use it a couple ways. The most straightforward way to use it on the cluster is to use Insight and run it in like a batch mode. There's examples of that on the Insight documentation, or we can help you with that. And it saves the performance data to a file. And then you can pull that file back to your own local Mac or Windows or Linux box and run the Insight GUI with the file post-processing after the job. And you can surf it and use all the fancy features of the GUI to look at that report. There's also like a text dump of what the report has in it, but the GUI will show you things that are really only visible through the GUI interface, like some of the timing graphs that you'll see there, the time series. So next. On the CPU side, we have AMD UProf, but that is not working yet. That's also contingent or blocking on our decision about how to handle hardware counters on a shared system and still get all the security model correct. Intel's One API Advisor is ready to run in more of a sampling way, and I've used it on the machine, and it's functional. It doesn't have the counters, but like the Insight tool, it does a very good job anyway, just getting all of your calls into the compiler libraries, and also following the types of instructions that you're issuing on the CPU side. So you can use the Intel One API Advisor out of the box with the Intel compilers on the CPU side, and get things like roofline plots of how you're using the memory bandwidth and the CPU cycles and flops. Next slide. Quite a few community codes and libraries have been installed on the system, and much of this has been with SPAC. So we're using SPAC when possible, because SPAC packages up an install of a library or an application for us and gives us good metadata and some ability to reproduce a build. So if we need to do SPAC again on the same package with a different compiler, we have a good idea of how to reproduce that build. Also, SPAC is a little bit of a hands-off, unattended install once you get it going. So when SPAC is working well for me, I can get more done, more installs done in a given period of time than manually configuring installing. Now, that said, sometimes SPAC doesn't work. And so we do have packages that we've built, like in Software External, that you'll see that are built the old-fashioned manual configure way. That applies to some things that SPAC just wouldn't build correctly for us, or if something's in very early beta version and spec doesn't have a recipe. We did this for the current OpenMPI 5 beta series of OpenMPI MPI implementation for the MI100 node recently. Spec doesn't have the recipes for that yet, so I've just followed a different page that AMD had and built those manually. Next slide. Greg's been chiming in on the licensed software questions. Good. Open on demand. So we do have an open on demand implementation to go with Delta, and this takes the NCSA identity. The interactive apps there today for you are Jupyter, and then I just updated the documentation this morning, remembering that that's also a good way or an alternate way to get a SSH shell. So Open on Demand has like a little piece up under the top under clusters where you can just say, I want a shell on Delta. It'll pop you into an SSH connection that's going to be sort of the standard SSH from Open on Demand for anybody. So if you were someplace where you didn't have a SSH client, but you had a web browser that you trusted, then you could still get into the system that way. For Jupyter, our most common question that we get, we've tried to address on this slide. It's also the most common question we get just in the general batch setup. Take care to match the name of your account with the partition you're trying to use. So all of your account names have CPU or GPU as a suffix, and the partitions have CPU and GPU in the names. So you want to use CPU accounts with CPU partitions and nodes, and GPU accounts with GPU partitions and nodes. Get that right, and then Jupyter just starts right up through Open on Demand. Next. So Greg talked a little bit about the science gateways that we're currently in testing phase and things that are starting to be spun up on Delta. He's working with a group in San Diego on one of these, and that's something we're interested in helping with and establishing more of these on the system. Also on Open on Demand, if you need help with customizing your Python in that environment, we have a separate page off of our documentation. If you go to the Open on Demand area on the main documentation, there's a new little link hiding in that area that'll take you to customizing your Open on Demand experience. So you can set up R, you can use the virtual environment that you want to use with Open on Demand and use everything with Jupyter Lab. You can go crazy. Yep. And then I fixed the link here the other day, so that top link is our recommended link. The next one is the one that you would find if you dug around on the Access site, but use the top one for the main Delta documentation. That's the one that we're updating. That, you know, if we make a change to that this afternoon, you'll see it. The other one lags in time a little bit. It's not really alive. And then there's the previous version of this training in a YouTube video, if you want to play that back. And I think Sandy will have this one up recorded fairly soon as well. Are we at the end, Greg?
Yes, we are. Thank you, Galen. All right, so we have a little bit of time for specific questions if people want to bring them up. We're happy to address those questions now, or you can post them in the chat. you can send us an email. So one thing we didn't describe, and something that we need to add, is ways of contacting us. And some people on the session today are already aware of some of the features that Access provides. So if you're coming in through an Access allocation award, Access through the user support award led by the group at UC Boulder, have enabled some interesting functionality. There's you can go and submit, if you want to submit a ticket for Delta with respect to the Access program, there's a web form available through the support page that'll submit a ticket into the Access RT ticket system, which we'll look at, and we will look to see whether it's an issue with Access or an issue with Delta itself. And if it's an issue in which it falls under more the activities for people on Delta, like the user support team, we might move it ourselves or ask you to submit the ticket to our local help at NCSA ticket system. There's also what's called the Access affinity groups for getting more information. If you subscribe to an Access affinity group for Delta, you'll see that there is a Slack Access community Slack forum available, and there'll be each resource provider will in principle have an affinity group Slack channel for each resource they have. You can reach out there. We would prefer to work with you in a ticket. I know that the intent is to kind of have group-based triaging and addressing of issues, but sometimes we want to make sure that the right information gets sent to you. So if you have a question, feel free to reach out to us by any way, but any means. But most detailed interaction will eventually be in the form of a ticket. All right, let's see. Some questions have come in while I was chatting. Could we connect to Delta by Visual Studio? Well, so Galen, how would you like to answer? Would you like to answer that one in terms of something like some of the other IDEs that we have?
Yeah, me and Peter are working on that in a JIRA issue. We're looking into it. One requirement for any IDE to connect to Delta is that it's got to support two-factor authentication. And I have run into an IDE already that does not support two-factor authentication. Mm-hmm. So if the SSH client built into an IDE is not flexible enough to be reconfigured, to do password and have a second factor, a lot of times it's just that they need to add a second box in their prompt. But, if the IDE doesn't support that, then you won't even be able to connect. So we'll look into it, but we're not the Microsoft help desk, so there's only so much we can do there.
Right. Okay, great. I'll take the next question. So the next question, oops, what happened here? Just kind of scrolled. Is about different queue and shorter wait times to test jobs for benchmarking or so we would recommend the use of the interactive partitions. The interactive partitions have access to all the nodes for the regular partition plus 2 extra nodes for quicker access. So for example, if longer running 48-hour jobs are filling up let's say if they're the 100 A100 nodes, if they're filling up those, there'll be at least 2 nodes available for grabbing a quick GPU or 2 for a period of time up to an hour. So our recommendation is to use the interactive queue for that. And if you have unusual demands and unusual benchmarking requirements or other really short prompt, I know some sites have what are called prompt queues where they actually hold aside resources. Those typically are not allocated in a way that they control usage, and so that you often have to compete with other people in a very shared overloaded system. So we prefer not to do it that way. So hopefully the interactive queue should be very responsive for you. All right, next question from Lynn Go is, what's the relationship between Delta, HAL, and Blue Waters? Well, all 3 are housed at NCSA, so that's a commonality. One big difference is Blue Waters was decommissioned earlier this year. This basically the beginning of this year, Blue Waters was decommissioned. All three are funded through NSF in one form or another. Blue Waters was a leadership class system funded through a separate call for proposals. HAL is an NSF funded resource through an MRI program, and Delta is also an NSF funded resource funded through a more recent Track 2 solicitation. Other than that, there's nothing that connects them together. HAL is logins based on if you're part of the University of Illinois, based on your net ID. Accessing HAL, accessing Delta is based on a separate identity, NCSA identity. All right, Andrew has a question. So I don't know, if we got back to your Radiant question, but we can also talk to you about that later. In cases where app doesn't support two-factor, you can often do SSH telling. That's true if the app doesn't, but you still have to use SSH to do two-factor. So basically, the requirement is with Delta, the only way you can get access to it is through two-factor, even through Open on Demand. We do make some exceptions for gateway projects. So we will have gateway projects that cannot use two-factor because there's no strictly a person. There's a community user account, and that community user account does not have a two-factor associated with it. So there are only a handful of exceptions for that. And that's a good point. What is the ranking of Delta? See, Abdul, I guess you're assuming making an inference about top 500. We don't have a way of running the HPL code across all resources on Delta. It's too homogeneous and heterogeneous. And so we are planning to submit a number based only on the A100 by 4 nodes, and that would put us somewhere just outside of the top 100 systems, probably, if you look at percent of peaks and stuff. But a lot of it depends on our upgrade on the network that Brett mentioned earlier to get better performance. Tours, that's another good question. We don't know. We can do tours by special arrangement. At the moment, I think we don't have a general tour program like we did when we were hosting Blue Waters. All right, I think Galen answered Anna's question. So you have to kind of know you have to log in. All right, okay. How are we doing on time, Sandy? Are we good?
Yeah, it's at 2:20, so.
All right. We've been slowly losing participation, so I think maybe we will wrap things up. If you have additional questions, feel free to send them in through the different mechanisms, either through Access, submitting an Access ticket, or through NCSA directly through help@NCSA, and we're happy to communicate with you. All right, thanks everyone. Thanks to Galen and Brett for presenting, and thanks to Bruno and the rest of the support group for answering questions in the chat. And we'll wrap things up, and Sandy will send out a link to the recordings sometime soon. Thank you, everyone.